Seats, warm welcome. My name is Robert Dijkgraaf. I'm the director and Leon Levy professor here at the Institute for Advanced Study. It's a great pleasure to welcome you to this kind of lecture and panel discussion actually at the occasion of our Board of Trustees meeting. So it's always a particular pleasure to welcome the many trustees here tonight. We'll have the topic tonight is machines. How do they learn and where are they headed? And although the topic will be about self-learning machines, I'm very happy that we have some human beings tonight on stage to discuss this. In particular, we have a great pleasure to introduce to you Sanjeev Arora, visiting professor in the School of Mathematics, and Richard Zemmel, visitor in the School of Math. And this is part of a very exciting program that we have actually just started. We'll be here for the next 3 years. Sanjeev will actually be running it about machine learning, the theoretical underpinnings of machine learning. It's based in the School of Mathematics and it is supported by our trustee Eric Schmidt and his wife Wendy. And so we're very happy that we'll have this group of postdocs and visitors at the Institute working on exploring these mathematical underpinnings of machine learning. It's of course a topic that's very much in the news, not only in the news, I think to a large extent determining our lives. So I think there's a lot of interest in this. And I should also say, although he can't be with us tonight, that Avi Wigderson, the Herbert Maas professor in the School of Mathematics, who runs our computer science and discrete mathematics program, of course, very much also involved. Just to introduce tonight's two speakers, they will both give a rather short presentation, and we'll have a kind of a panel discussion. Of course, also want to invite you at some point in that debate. I'm sure this will trigger and has already triggered many questions. So brief introductions of the two speakers. As Sanjeev Arora, he is actually has a joint now appointment at Princeton University. There he is the Charles C. Fitzmaurice Professor of Computer Science. Aurora's work has earned him many awards. Just mentioned the Fulkerson Prize in Discrete Mathematics, the ACM Infosys Foundation Award in Computing Science, the Gödel Prize. He, after receiving his PhD in Berkeley, Arora joined the faculty of Princeton University, has been there since 1994, and of course visiting professors at many different institutions. He was the founding director and lead principal investigator at the Center for Computational Interactability, and he was elected as an Associate for Computing Fellow in 2009 and also Simons Foundation investigator. Rich Zemmel is actually at the University of Toronto. He's visiting here. Again, very influential researcher in this particular area. Many awards. I'm mentioning some NVIDIA Pioneer of AI Award, 2 NCERC Discovery Accelerator Grants, Young Investigator Award, Presidential Scholar Award, and 7 Dean's Excellence Awards at the University of Toronto. He obtained his PhD there in 1993 and has been a professor of computer science and a faculty member since 2000. Rich received his bachelor's from Harvard, was a postdoctoral fellow at Carnegie Mellon and the Salk Institute. He is currently the research director of the new exciting Vector Institute of Artificial Intelligence at the University of Toronto, one of the centers for machine learning. He's a fellow of the Canadian Institute of Advanced Research and is on the executive board of Neural Information Processing Society. He's also co-founder of Smart Finance, a financial technology startup specialized in data enrichment and natural language processing. So I think, in some sense, we couldn't have a two better kind of people to introduce this exciting topic to us. So we'll have 2 short presentations. I won't intervene, and then we'll have a panel discussion here. So I would like to invite Sanjeev, and it's such a great pleasure to have you here on campus these years to start the discussion. Thank you very much.
Thank you, Robert. It's a great pleasure to be at the IAS for the next few years. So in this talk, well, I should give you the good news that there are no formulae. I was told not to have any formulae. It's a popular talk. And that's my usual joke, that machine learning is really self-improvement for dummies, dummies as in dumb hardware. So now, of course, all of you have seen machine learning in the news. These are just the covers of Science and Nature, two leading journals in science, about learning. This is about Go playing. As you probably read, earlier this year, the computer beat the world Go champion. Cards, self-driving cars. Computers are now better at spotting cancerous tumors in X-rays than humans for many kinds of tumors. This is machine translation. Sorry, it's not a great graphic, but yeah, machine translation has really improved in the last couple of years. And machine intelligence covers saying AI is transforming science, artificial intelligence is transforming science. So it seems very fancy that machines are becoming intelligent, but operationally speaking, what's going on is something very, very simple. Okay, and that's what I want to highlight in this talk. That machine learning, the core idea is very, very simple, and it's trying to search for patterns in data. And this search for patterns is what drives all the other applications. Okay, so for instance, if you're learning how to drive if you're trying to train a self-driving car, you let it run a lot, watch the human, and it looks at the data and finds some patterns. Okay, so how does this search for patterns works? And it relies on a very old idea, curve fitting. Okay, it's this theory, in some sense, always existed, but was put on a scientific basis by the mathematicians around 200 years ago, notably Gauss, and he came up with something called Gaussian fitting. So here's an example. So for instance, economists plotted inflation and unemployment. These are actually figures from Japan over many years, and they found this curve, which they then found for other countries as well. So this is the famous Phillips curve in economics. So that's an example of curve fitting. The data points don't lie exactly on the curve, but you find a curve that best fits those data points in the sense of Gauss, and that's your curve. So you can think of this as finding the pattern that exists between, or that connects inflation and unemployment. Here's gas law, which you may remember from high school chemistry. Sorry, there is an equation there. But the point is, you examine the pressure, volume, and temperature of a gas, and you vary them, and you see the surface. Now, this is a surface because there are three variables, pressure, temperature, and volume. And you plot them, and you get some kind of a surface instead of a curve, and which happens to be that. So machine learning is basically this, surface fitting with many, many more variables. It's not two, not three, sometimes hundreds of thousands or millions of variables. So this surface fitting is used to learn patterns of data. Okay, so maybe all of you have an intuitive sense for how this works for scientific problems because you saw these in high school science or math. But how does it work for something that looks like intelligent behavior? So here's a very simple example, learning to rate movie reviews. Okay, and I chose as an example a recent movie by a local boy, Damien Chazelle. So these were actual reviews I saw on Amazon. So one is, so the rating actually I made up. The Amazon ratings are on a scale 0 to 5, but I made it on a plus minus scale. So this one said slow moving, couldn't get into this movie despite all the awards it has won. And the other one said, wow, did not know what to expect and was delighted, loved the homage paid to the musicals of old. Story was good as well. All right, so in this data set, the reviews consist of text, and there's a numerical score, a rating. So the task we want to solve, that we want the machine to solve, is, well, it's given some training data, so millions of reviews for different movies, so text like this, and accompanying rating score. And from that, data set, it has to learn to predict the rating score from given the text in a new review. Okay, so it's given these millions of reviews with a human rating, and then after that it just sees a review online or whatever, and it has to come up with a numerical score. Okay, so we saw these examples on the previous slide where there was a law of gases or law of inflation versus unemployment. So what is the law of movie review scores? Okay, and it seems like in order to come up with these ratings, the machine has to somehow understand language, right? Okay, so now let me tell you a very simple technique that works really remarkably well, okay? Much better than it has any right to. Okay, so you have some text like this, right? And from this text, the machine has to generate a rating, a score. So the idea is going to be the following. Well, there are, let's say, 500,000 words in the English dictionary. Now, this is not in your normal English dictionary, the one that's actually in print, but this is some conceptual English dictionary where you have strange contractions, misspellings, etc., which you'll find in real data. Okay, so if you include all of those, you easily reach a lot of words, 500,000, 1 million. Okay, so the hypothesis is going to be very simple. We are going to assume that the sentiment or the rating derives from the sentiment scores of words in the review. So the hypothesis is that each word has a sentiment score. The machine doesn't know this yet, but that's the hypothesis. Okay, just as gas has pressure, volume, temperature, a word has a sentiment score. And the review rating is just the total sentiment score of all words. Okay, scale to, let's say, -3 to +3, if the ratings are from -3 to +3. Okay, very simple hypothesis. Okay, so each word has a sentiment score, and the overall sentiment of the review is just the total score scaled appropriately. Now, the machine, this is the hypothesis, this is the model. The machine doesn't know these sentiment scores. But turns out that finding the sentiment score for 500,000 words is some kind of a surface fitting, which I won't write the formula for, with that many variables. And it can be solved with modern machines and algorithms given a few million ranked reviews. Now, these are enormous numbers for humans. It would take you a lifetime to go through 1 million reviews. But for a machine, it can be done in a few minutes or less. Okay, so just to emphasize what's going on, or to give you an example. So that's a hypothesis. Each word has a sentiment score. Review rating is total sentiment score of all words in it. And so after you do the surface fitting, you get some kind of a table where for every word, there's a sentiment score. Okay, and in this table, you see that as of these words are not meaningless. They don't have much of a score. So this is actually scores that my student came up with. He ran these through the training program, and he gave me these numbers. So as you would expect, words like as, the, of, they don't contribute much to the score. And something like loved has a very high score, 1.1. Good has a high score, 0.6, etc. So now you input, if the machine is given a sentence like this, it just looks up the scores that it has learned for these words and takes those scores, adds them up, and gets 2.7. That's it. Okay, so that's its prediction. So that's it. Very simple model. Okay. I hope you are still with me because this is very simple. And if you are, congratulations, you've completed week 1 of undergrad machine learning that we do, okay, the first week. Very simple, linear classifiers. Now, the point is, this seems very, very simple, but actually it's shockingly good, okay? On these kinds of tasks, it actually does shockingly well. It's pretty hard to beat it with more complicated techniques. And the reason I chose this example is that general machine learning is very similar, okay? It's a more complicated model. It's not a linear model like this where you just add up things. But the idea is similar, okay? And there are some variables that you find, and then you use those to arrive at a decision. Okay, now you ought to be thinking that this is a really simplistic model, right? The total sentiment score of all words determines the review. And you're right to think that because this is not how we humans do it, right? So for example, a really stupid thing about this is that word order in the text does not matter, right? Because the total sentiment score is just the sum of all the individual word scores. So word order does not matter for the total score. Okay, so this classifier is this decision program is very easy to fool. For instance, no good versus good, comma no, would have the same score. Okay, it's the same words. So the sum of the scores is the same. So indeed, this is a big problem with machine learning that the machines currently are actually easy to fool. They just work very well if the data is not unexpected, okay? So, but if you want, you can actually fool them. And this is actually a major research problem to fix that. The second thing you're probably thinking is, this machine needed millions of examples to learn what is or is not a positive movie review. None of us had to read 1 million review examples to know that, because we understand language, okay? The first review we saw, we could tell, is it a positive or negative review? We don't need to train with 1 million examples. Okay, so what exactly does it mean to understand language, right? So you would imagine that no-brainer, right? You should train a machine to understand language, not do this kind of simple sum of scores kind of classifier. So clearly you want machines to understand and formalize language. Now, believe it or not, that's what machine learning or artificial intelligence was trying to do for many, many years, okay? Using the kinds of tools that science has thought are important in this domain, namely logic, grammars, model theory, etc. And it seems like these should still be useful, but actually it's not been so easy to incorporate those in machine learning. So the question is how can machines understand language? Now, of course, understanding is a very nebulous word, so let me just show you one simple technique. So the idea here is unsupervised learning. And the idea here is that, okay, for instance, Amazon has a lot of movie reviews, I don't know, a few 100 million, but that's still not a lot compared to the amount of text that's out there. All the newspapers, all the blogs, all of Wikipedia, etc. So unsupervised learning is a method to just read through a lot of text, which is not labeled by humans. It's written by humans, but it's not labeled in any way, and somehow help the machine understand language. So what does that mean? So I'm going to give you, again, the very simplest example of this, not the complicated models, and in Rich's talk you'll see some more complicated models. So the key idea is to train machine to predict part of the text from the adjacent text. Right? This fits in classic scientific tradition, right? When do you understand a phenomenon like behavior of gases? When you can predict what happens. So, this has intuitive appeal, and so that's the idea, that you train the machine to predict part of the text from the adjacent text. Okay, so it tries to fit some kind of a model for this. So in other words, unsupervised, there's no such thing as unsupervised learning, it's really supervised by the data. Okay, you just take text written by humans and you're training the machine on it. So an example of this is sentence completion, right? I went to a cafe and ordered, and everybody here can come up with a few completions, coffee, bagel, whatever, but you would not say baseball bat. So it turns out machines can learn to do such completions very well by analyzing huge amounts of text. And in learning to do so, and maybe you'll see that a little bit more in Rich's talk, they implicitly pick up a lot of grammar sense, etc., so that they can start to do translation, question answering, etc. Okay, so just a little bit more detail. How does it try to predict the part of the text from the rest? So the assumption is, so in this model for prediction, you assume that every word is represented by a vector with 300 dimensions. The 300 is not important, it's just a vector, okay? So instead of a word being one number, as we had in the previous example, right, the sentiment score, the word is represented by a vector of numbers, okay, 300 numbers. And you can define an affinity between two words, namely the inner product of their vectors. It's not important what that is, it's some operation on vectors. And now there's a hypothesis that the probability of the word being in a certain place in the text is determined by its average affinity to the previous 5 words, let's say. And I won't put here, because I don't want to put a formula, the precise functional form, but it's not a very complicated form, okay, of this formula. What is this probability? So this is some kind of a probabilistic model, which, if you think about it, you need, because in the previous slide you see this, you can complete a sentence in multiple ways. So there's always a probability distribution of the next word. It's not a unique thing. So the machine just tries to make sure that this probabilistic law is sort of tracking or predicting well the words that actually occur. Okay, so now finding the best word vectors to the above probabilistic model is some kind of a surface fitting problem. Well, there are 500,000 words. Each has 300, is represented by a vector of 300 numbers. These are massive numbers. You know, it's something like 150 million variables. Okay, it's huge, but the good news is this is tiny for even your laptop. Even for your, these days, even your smartphone can hold this. Okay, so you solve the surface fitting problem, you get these vectors, and then these vectors turn out to be very useful in question answering, machine translation, etc. So this is just a taste of how unsupervised learning works, okay, where the machine has no goal in mind, just trying to learn the structure of language. So summary so far, machine learning involves finding patterns in data. I gave you 2 simple examples, but all the other examples are conceptually very similar. And this finding of patterns is some kind of a surface fitting involving a large number of variables, but that fitting is relatively easy for modern computers. So now you may ask, well, Gauss knew about surface fitting. Why is this successful now? So firstly, as I said, there were false starts in this field. In the 60s, 70s, 80s, people were trying to use much more complicated techniques, using logic, grammars, etc. And somehow the simplest scheme works best. And why is it successful now? Well, there's some kind of a symbiosis between 3 things, namely data, algorithms and hardware, and commercial payoff. And, well, data, clearly, you need. Algorithms and hardware you need to solve these problems very fast. And commercial payoff, as you all know, the leading companies today are tech companies which derive tremendous profits from these kinds of algorithms. And that creates a symbiosis, because all those companies, because they have these snazzy applications, these smartphones and so on, then can collect much more data to train the algorithms, right? Which allows them to also invest in better algorithms and hardware. You know, they hire a lot of our PhDs and machine learning experts, which in turn drives more commercial payoff. So there's this symbiosis going on in the tech world for the last many decades, and right now it's going on in machine learning. And so now to address this issue again, none of this is remotely how humans think, right? So the first answer is that the imitation approach, it has not worked very well in the past. Okay, think about how we learned to fly, right? Airplanes, or play chess, Go, etc. It was not by imitation. You had to design completely different approaches, different from the way nature does it, or humans do it. And the second, even more serious answer is that we have at an operational level, no idea how humans think. We all clearly think and communicate, but we have very little idea of how humans think. So, so it's not clear how to leverage that. And all the past approaches, for instance, trying to do machine translation or so on, by our conception of how humans think, that just didn't work. And instead, this kind of curve fitting or surface fitting worked much better. And in fact, given that we don't understand at an operational level how humans think, turns out machine learning is currently the best hope for figuring out how humans think. So let me give you, there are many, many people working on it, and this is just a slide about some paper we did this year with colleagues in the Neuroscience Institute. So just to give you a sense, so people are trying to understand how the brain works, and one technique is fMRI, which measures blood flow in a person who's awake and who's given some stimulus. This machine is measuring blood flow in something like 50,000 points. Okay, so it's tremendously data intensive. It produces a lot of data. So now this person is awake and alert and is given some stimulus. In this case, was watching episodes of Sherlock. Sorry, the movie scenes. Sorry, not episodes. Movie scenes. So there's data being produced. Okay, these are the vectors of responses, the blood flow at 50,000 places in this person's brain. So these are the responses, and that's movie scenes. And now you want to somehow understand how this data relates to that. Okay, so set up some kind of a decoding problem to go from here to there and vice versa. And this is a very difficult problem. And these colleagues came up with the idea, the neuroscience colleagues came up with the idea of annotating these movie scenes by text. So a person annotated with this text. And then they asked us how we can now represent this text, and that we actually happen to know using some of the ideas I was talking about, how you can represent meaning of text. So we applied those ideas, and we were able to set up some kind of a mapping, okay, which gave some insight into theories about how the mind works. So I just want to give you some sense for, when you want to understand the brain, you have these very, very data-intensive experiments, and you want to make sense of it, and the only way to make sense of it is machine learning. Okay, so some concluding thoughts. Intelligent machines is an old dream, of course, and people at Princeton helped set us off in this direction, people like Turing, von Neumann, and Gödel. And it's becoming a reality thanks to reams of data plus fast optimization methods. And here, too, Princeton folks have been pioneers. Tukey, Kuhn, Danzig had strong Princeton affiliations, and many others. So it's really a pleasure that the Institute is now heading in this area. And so I expect rapid progress, including here in Princeton. Thank you very much for your attention.
Hi, everybody. It's my pleasure to be here. I am visiting this term, and I'm hoping to visit for the next several terms to be part of the machine learning focus at the Institute, and I'm really looking forward to it. My usual home is at the University of Toronto, and also, as was mentioned, the Vector Institute there. So I'm going to tell you about a particular kind of machine learning. So we're drilling down a little deeper into the field of machine learning. I'm going to focus on deep learning. And the key idea I want you to focus on here is think of learning representations. So if you think about what Sanjeev was talking about for the words, you're going to have this, he talked about it as a 300-dimensional representation that's going to allow you to predict, if you have one word, it's going to allow you to predict the words that come right before or right after that particular word, right? So the question is, how are we going to learn those 300-dimensional representations? And I'm going to talk mostly about a particular approach called the neural network. That's one kind of machine learning system, and it's the one that has been the most successful. So all these successes that are made the cover of the magazines and that Google and Facebook, et cetera, are very excited about, almost all of them are about neural networks. So neural networks have actually been around a very long time. They were studied, there's ideas about them back in the 50s, and so they've been around a long time. Some of them, and the name neural network comes from real neural networks like brains. So it was inspired by biology, where the underlying idea is that the main processing unit inside your brain is a neuron. And neurons, this is a little schematic of a neuron. Its nucleus is here. It takes in input, impulses that come in along dendrites that connect from other neurons into this neuron. And it sends out impulses, electrical impulses along its axons that then go and connect and become onto the dendrites of other neurons. So communication is going from one neuron to another through the dendrites and axons. Our brains contain roughly 10 to the 11th neurons, and each one of these communicates or connects to around 10 to the 3rd or 10 to the 4th other neurons. So this is the inspiration for neural networks, where the idea was, instead of thinking about a standard computer like with a central processing unit, now we want to have this more distributed thing. We've got tons of neurons and they're all talking to each other. Right? So that's the setup, and that inspires the idea of a neural network. But it quickly becomes abstract. You lose all of these, the details of the neuron, and you replace it by a little circle here. Okay? So this is a neuron, a little circle here. It's called a unit in an artificial neural network. And the idea would be that this would be a neuron that gets its inputs from other neurons through these arrows here, collects the activity, and then sends output to other neurons here. So that was the abstraction of a neuron. And the way a neural network works is that there's some set of designated neurons or units that are called the inputs. So that takes input from the outside system. And then there's some set that are designated as outputs. That produces outputs or predictions. Okay? So this could be, if you're doing something like sentiment analysis, each word would be represented by one of these circles, one of these dimensions here, one of these units in the input. And then the output, you can imagine that you want to say, is this movie review positive or negative? Thumbs up, thumbs down. So thumbs up could be this one, thumbs down over here. All right? And so what you have is a lot of data where you say, these were the words that occurred, right? So how often did the word good occur? How often did the word, horrible occur? So there's some count in the review of how often each word occurs, and then the output is whether it was overall a positive or a negative sentiment for that review. And then there's a lot of processing that goes on in between the input and output through a set of what are called hidden layers. And these hidden layers, the idea is they're going to have weighted connections, and the weights are the things that are actually going to be learned. They're going to be kind of, think of those as weights to say, what's the strength of the connection between this neuron and this neuron? And those are going to be learned. And so these are going to represent features of the inputs. So for instance, if you take in an image where this is, each pixel now is one of the input units. So let's say, your camera takes megapixel images. So each one of those pixels would be a separate input into this neural network. There would be weighted connections that go through, and at the output it might be recognizing, the person that you just took a picture of and classifying who that person is. And along the way, there would be a lot of features that are calculated to say things about like local features, like what are the edges in the face and other things that it's seeing. Okay? So that's what a neural network does. And a deep neural network, which are the most common ones these days that get the best results almost universally, are the case where you have several levels of hidden features. So deep just means you don't go directly from the input to the output, but instead you go through several processing levels until you get to the output. But it's the same basic computation at every step. So training neural networks means, as I said, you want to set the weights or set the values of those connections so that the network produces the right answer on a data set, on a training set. So this is meant to be an example of a very simple training set where you'd have, each one of these would be an image. So think of this as there's a bunch of pixels, some of them are black and some of them are white, and we know the right answer for that one should be that this is the digit 0. Over here, this little image, a bunch of black and white pixels, the right answer should be a 1. Okay, so for every one of these images, the network should produce the answer between 0 and 9, right? One of the 10 digits. So these are 0s and 1s, these are 2s, it's a funky 3, some 4s, and a 5. These are actual handwritten digits that the network would have to learn how to classify. So now and this also motivates the idea of doing machine learning, because it'd be very hard for someone to sit down and write down a bunch of rules that would say, oh, this is what makes a 2, because look at all the variety of 2s that are there. It's very hard to just write those down as a set of rules. Instead, you throw it in a neural network and let the neural network perform its magic and try to figure out, for this particular image, which digit is it, okay? And like Sanjeev, I'm not going to show you any equations, but I am going to reference some high school calculus. So the way you do this is by calculating derivatives, okay? So you're actually going to calculate derivatives and use an algorithm called backpropagation. That's the workhorse that's being used in all of the successful applications of neural networks. And all that is really, if you remember your high school calculus, it's the chain rule. So it's applying the chain rule to calculate derivatives in a neural network. Okay, so now let's think about how to apply these things. And the standard kind of most successful application of neural networks has been for object recognition, where you want to take an image and recognize what object is in it. And this is an interesting case because it's one of these cases where people are very good at it. It seems like something that comes natural to us. But computers, for a long time, have been horrible at it. They can't do it very well at all, until recently. So one question is, why is it hard? So here's some examples that make it hard. So you want to recognize this animal, he's behind a branch, he's deforming his face, in a very cluttered environment. It could be nighttime, an odd viewpoint. So there's lots of different ways in which recognizing this particular object is hard. Right? And then there's other things. There's a lot of variation within a class. So all of these things are chairs, right? And you want an algorithm to say, yes, this is a chair. And some of them are kind of classic chairs, but some of them are kind of odd, right? I mean, who would think that this is really a chair until you study it a bit? And then there's a definitional question, right? So is this a chair or not over here, right? So this is something that is a good challenge. And so how are you going to try to solve it with machine learning or with deep learning? You're going to build a data set. You're going to have a lot of examples where you're going to say, here's an image, and here's the right answer. Here's an image, here's the right answer. So there's a famous one of these that's called ImageNet. ImageNet, there were 1,000 different classes, so 1,000 different kinds of objects to be recognized. And each one of those had around 1,000 images that were used for training. So you get over 1 million training examples and 150,000 tests. So that's to capture the 1,000 training examples per class, is to capture the kind of variety you have to handle when you're doing recognition. And the classes included some things like flowers. You can't see it where you are, I'm sure. But flowers and vases and clocks and all kinds of things. And also it got very specific. Different breeds of dogs, for example, that were very challenging. Right? So this had been out there for a long time, and people were banging away on it, particularly in computer vision. This has been a problem that's been attacked for a long time. And about 5 years ago, some colleagues of mine down the hall in Toronto came up with an algorithm based on deep neural networks that beat the socks off of everybody else. So this is what happened that year. These are the other methods that were out there. And the best methods we're getting, this is how much error there is. And so you can see that the best method was getting an error just over 25%. All right, that doesn't sound very good, but it's 1,000 classes, so it's a hard problem. Right? So 25% is not too bad. This method, the neural network, which had the clever name of supervision, so it's the idea of as supervised way of training it, and it got down to almost 16%. So you can see this gain of 10% was a huge gain and really got people's attention. Right? And what was that built on? That was built on this idea of a deep neural network. So the neural network took as input, as I showed you. This would be an image of a cat, let's say, that was 224 by 224 pixels. That's how many units are there. And it goes through several layers of neural networks, different kinds of units, hidden layers, as I showed you before. And then at the output, there's 1,000 different units, one per class, and the right answer for this one is cat. Okay? And you train it up. But then one thing I want you to think about is the second to last layer here. Not the last layer, but the second to last layer is interesting because it is a representation of the image. It's not saying whether it's a cat or not, but it captures all kinds of interesting information about the image. I'll get back to that in a second. So this same approach now has been used in all kinds of other problems. It's the workhorse in your cell phone doing speech recognition. It was a workhorse for Go, for anything which is trying to recognize things in images, like down to the pixel level. It's a workhorse for autonomous driving. This is a fun version that somebody did where you can take a photo and then redo the photo in the style of some painting. So like a Van Gogh stylized painting here. I mean, a photo here. So what's interesting, I think more interesting than the results that have been found, is that if you decapitate the network and you cut off that last layer and go to that one I was saying, the second to last layer, that it's a very useful representation, it turns out, for lots of other tasks. So it's not just useful for recognizing those objects, but in many other instances, for other kinds of things. So this is using that representation to go in and find within an image and do a good job of detecting individual kinds of objects here, down to getting 92% right on the bowl and cups and all the different objects in here. And so with my group, what we did is, well, let's try to do this same type of thing where we want to now combine it with text. So this is going to be tied back to what Sanjeev was talking about. We're going to take sentences and look at the form a representation for sentences, and we're going to take images and form a representation for images, and we want to put those together. And you might want to put those together if you want to do captioning of images. So you take an image, and what we would like to do is the system should say, a good caption for this image is a castle and reflecting water. Over here, a ship sailing in the ocean. So this is another kind of prediction problem, like Sanjeev talked about, where you can take a word and predict the words around it. This is a little different. We're going to take an image and predict the caption. And we're going to take a caption and do it vice versa and predict the image from that. And the way we do that is by mapping them to the same joint space, to forming the same representation. In that case, it was a 300-dimensional representation. This is more like several thousand dimensions. But it doesn't matter. It's still the idea is that they're in the same joint space, and proximity is what matters. This image should be mapped to a point that's close to its appropriate caption. That's what the learning is doing. Okay? The same type of approach actually is the most successful thing that's being done now for machine translation. Rather than doing images paired with captions, in that case you have, let's say, English sentences and French sentences, and they're trained to map to the same locations. Okay? And then we want to go a step further. We want to actually generate captions from this. That is, not just associate captions and say this caption goes with this image. I'd like to be able to show an image and then have the machine spit out a caption of its own, like make up a caption, word by word, make out a caption. And it does this by a bit the way Sanjeev was talking about, where you say, what's the next word? What's the probability over the next word? Choose a word. Then, given that word and given the image, what's the probability over the next word? Choose a word. And you keep going, just generate word by word, and eventually you get a caption out of that. Right? So that's the way we generate novel captions. And let me show you some of the captions that we generate in this way. So here's an image, and you say a car is parked in the middle of nowhere. So that's what the machine came up with. All right? A wooden table and chairs arranged in a room. A little boy with a bunch of friends on the street. Okay? So it does well in general. These are a bit cherry-picked, but it's fun to look at the failures, right? So this isn't going to be perfect, and one thing you should know is that these deep learning systems aren't perfect, and we can talk about that a little bit later, concerns of safety and things like that. But in captions, it's okay. We can come up with bad cases and not be worried about safety. So these two birds are trying to be seen in the water. And it's hallucinating a giraffe here. And this is an interesting case. So it says a woman in a bottle of wine in a garden. The thing is awful at gender. And so at the opening of at the Vector Institute a few months ago, we had a lot of dignitaries there. So the Premier of Ontario, the province, the Mayor of Toronto, the Finance Minister of Canada was there, and the three of them stood in front of the camera. And I tried a live demo, took a picture of them, and it said, 3 men wearing a suit. And the problem is that the Premier of Ontario is a woman. And she said, well, maybe it's because I'm wearing a scarf or something, so that was all right. And then you can do something fun now. So this is trained in general, like we have lots of, how do you get the data for this? You need a lot of data. This is data from people just uploading images to Flickr with whatever they've written about it. Okay? So there's a lot of captioning data. We can also train the image part of it somewhat separately on lots of text. So like the movie reviews, we can also train it on books and other things. So then what we can do is when we generate our caption, we can generate it conditioning on a certain style. Okay? So one of the styles we do is we train up a system that's only seen romantic novels. So that's the style that it knows about. And then we give it an image and we say, okay, go generate a caption in the style of a romantic novel. Okay? So this is what it says. We were barely able to catch the breeze at the beach. Felt like someone stepped out of my mind. She was in love with him for the first time in months, etc. Okay? And it goes on like a romantic novel will. And then we said, well, let's try, we also did it on Shakespeare, right? So just trained on Shakespeare. And then we said, well, let's try, on the other hand, we trained it just on Taylor Swift lyrics. And we took the same image and put in Taylor Swift lyrics and said, you're the only person on the beach right now, I don't think I will ever fall in love with you. And when the sea breeze hits me, I thought, hey. And then back to the romantic novels. I'm a fan of sumo wrestling, so I especially like this one. So the romantic novels, he was a shirtless man in the back of his mind, and I let out a curse as he leaned over to kiss me on the shoulder. He wanted to strangle me, considering the beautiful boy I'd become wearing his boxers. Okay? Okay. Okay, so there's been lots of successes, and as we said, these things are pretty good, but they aren't really understanding images and text. They're doing lots of association, pulling out interesting features. I mean, if you look at this, is actually the fact that he's kind of getting him, that he's kissing on the shoulder is interesting information that got out of there. But they are somewhat brittle. So here's an interesting example where you say, these images, you give them to ImageNet, the thing I showed you earlier that got the really good performance, that supervision. And now you just change this is the way you perturb the inputs a little bit. So you get an image that looks like this. So add this to this one, you get this image. Add this to this image, you get this one. So to us, these look very similar to their original images. But if you give them to that ImageNet system, it calls each one of these an ostrich. Okay? So it's brittle. And so this is one of the current limitations of the system. They aren't really understanding images and text. And there's some challenges ahead. One of them is that we want to get much better at figuring out how to formulate these networks and train them up in some way. Right now, the favorite method still for training is something called graduate student descent, where you take your graduate student and have him train as well as he can until he eventually gets good at it. Another challenge is readily learning new classes. This is something that people are very good at, but our machines so far are not good at. That's something that I'm very interested in research-wise these days. And then in terms of the real world, the things that matter a lot are these last two. Calibration, which means can the system really have an idea of when it's certain and when it's uncertain? So how well calibrated is that system? And interpretability, if we want to use these things in some sort of real decision-making systems, it has to at least, if we can't understand the innards of the system, we should at least have some understanding of how it performs in lots of different situations. Okay, that's it. Thank you.
I think that was quite a challenging topic and generated a lot of questions, certainly me. And I want to take a kind of chair's privilege to start asking a few questions. Perhaps the first to you, Rich. In some sense, was there a prediction in terms, you were saying, well, the enormous amount of data and computing power and perhaps the death of the neural network. Is there some way to gauge in advance when this method will become successful or not? Or is that just a surprise? And in particular, with all the other outstanding problems, is there some sense what kind of computing power we have to bring to bear upon a certain topic before it kind of gives away?
Right. So I would say one of the chief things is first looking at what data is present, right? So like what we were saying with the captioning or the machine translation, that's what's really important. If you don't have enough data to capture all the complexity of the problem, like we were saying, the varieties of chairs and all the problems with recognizing the different kinds of images, it's hopeless. So for instance, deep learning isn't very good in a lot of health applications now. It's good for reading medical images because there are lots of instances of images and people have gone in and annotated what's happening in those images. But in a lot of health applications, either because of privacy, so you can't get access to that many patients, or
so you say that the amount of data is basically
that's
lacking.
key. Exactly.
But even if you have the amount of data, for instance, machine translation, this was kind of a surprise, right? That in some sense it was so successful.
So I think it takes time to also formulate it in a good way. Like the whole idea of thinking of it as a prediction problem, like predicting one sentence from the next, right? So I think some of these, it's hard to predict when it's going to work or not, but I think it takes time often to come up with the right formulation. That's another key thing. It's not just the data.
Sanjay, what do you feel are kind of the intellectual challenges? As you said, something, this curve fitting has been around for many centuries. So in some sense, that's, I would say, almost the most kind of boring way to present the model. Or it doesn't look very intellectual challenging. It's just curve fitting in so huge space. Right. What do you feel are the more perhaps mathematical, intellectual questions that are out there?
One question is that actually we don't really have any algorithms with provable guarantees.
Provable guarantees?
Provable guarantees. So
it just happens to work.
When it works, it works. When it doesn't work, we have no idea what happened. Yes. And the grad students try other things. And what Rich said, grad student descent.
I mean, in some sense, we are almost, I think you made a point once, almost in the opposite of the way computers and algorithms were developed, which started in some sense with a theoretical underpinning and
that's right.
Even very negative results, such as Turing and others. But so there's no real analytic way to see what works or doesn't work.
Currently not. Yeah, I mean that's an active research area.
So what are the kind of questions you need to answer before even getting in that direction?
The algorithms, some measure of uncertainty, which the current methods don't really give you. Also, just looking at the problem, whether or not these methods would work at all in the first place. It's not clear when it works and when it doesn't work.
Rich, you mentioned, sorry, you want to say
I would just also say, what does it mean to work, right?
Yeah.
That's another question, right, which is, for a lot of these problems, we're trying to solve very hard things. So what does it mean to, have a good caption? So even that is not really a well-defined problem. So it's not as simple. Some of them are cut and dry, like, did you get the classification right or not?
Yeah.
But a lot of these things that we're trying to do in machine learning aren't as cut and dry as that.
I guess maybe, the point is that if you can't even define what a good answer is, how do you set up an optimization or curve fitting problem to get to that answer?
Yeah. Rich, you also mentioned the issue of kind of stability, and I think this is something, it's all kind of clearly probabilistic, and so there is some errors there. But I could imagine, certainly when these machines become more and more important in our lives, that this idea of stability, that just by changing a few pixels, it certainly becomes an ostrich or something. You don't want your self-driving car to make kind of mistakes like that, I guess.
Yeah. So it's a whole area now called AI and safety, which is exactly addressing this question. And I think a lot of it is driven by this thing that both of us mentioned, which is called an adversarial approach, which is thinking about if an adversary sees your system, how could he fool your system, right? And then you build your system in order to thwart the adversary.
I guess, in some sense, changing this pixel with an enormous effect, you have to just change the right pixel.
That's right. That's right. You have a smart adversary.
But there are many smart adversaries around there, right?
Yeah.
I think, is it something that people worry about? That this makes our systems much more vulnerable than even the traditional kind of algorithms and codes that we have?
Yeah. Well, I would argue that some of our systems currently are very fallible, and I don't think our current drivers are really trustworthy in all situations either, right? But we're going to hold our autonomous drivers to a higher standard, I think, than our current drivers. But I think that is, is a very important research area to figure out how to make it more robust. Is really what it comes down to against adversarial attacks.
Yeah. Sanjay, another question I have is that this is kind of learning and machine learning, but now if I learn something, I can usually explain it. It's the whole idea of education. That we learn something and we explain it to the next generation. I saw this was this kind of wonderful series of professions of the future in the Wall Street Journal, and one of them was called robot psychologist. And the idea was, well, you could think that a psychologist will be at some point a machine, but I think they meant that the machine has to be on the sofa to be interviewed, because to find the stability of one of these machines, it's the same way to find the stability of human being, right? But what are there ways to kind of tease out, in some sense, what the machine is learning, so that we can learn how the machine does this? Have any of you some ideas about it?
I think that's called interpretability of these neural nets or other models that you learn. And because there are millions of variables, we have very little idea of what individual variables mean. Unlike in my simple example, in the complicated models.
Is this going into this kind of in-between layers and seeing what's happening out there?
Right, for example. So, so what is being captured there and how do you extract out that information is not clear at all. And that's an active research area. And, but I agree with you. It seems like it's an essential part of intelligence that we not only can, at a gut level, sort of say something or come with some decision, but also be able to explain it. Yeah. And it seems like that's missing from current approaches.
I would add one thing, which is that people are actively pursuing this, and there's two different findings I think that are relevant. One is people look a lot at what it's called like attention mechanisms. The idea is that when the system is like trying to recognize something in the image, it's not looking at the whole image, it's looking at a portion of the image. And there's a separate attention mechanism that actually produces better results if you include that in the model. And then that provides a bit of insight into how the machine is working. You don't know the whole innards, but by looking at attention, you can see at least where it's focusing on. And the second thing is that people are working on what's called distillation. So you try to take this big complicated network and distill it down to a simpler one. A smaller one that mimics the big one, and the smaller one is more interpretable. So that's one approach people are taking.
You also mentioned at some point that human beings are very good to not only kind of curve fit, learn in our environment, but then we are able to jump out of that, right, and do something else. Like in art, you have different styles, can perfectly write in a certain style, but then we're able to jump out of it. Is that something that machines can learn, or have you seen this happening, where the machine kind of, or the algorithm took a step outside the box?
Well, outside the box as surprising, sure. They do surprising things, as Rich's examples.
Yes.
So,
some of these
but is it being
captions
smart?
were,
That's a different thing.
Yes.
Yeah, it can be artistic and kind of, like you can always add some kind of noise to the system that does something you don't expect. And you can call it art if you want, but often it's hard to know what's going on.